Mars will kill you. The only question is whether it happens in 1 minute or 1 year. And to be honest, the slow death might be worse. What I'm about to show you will make you question everything you've heard about colonizing the red planet. And here is a question. If you could bring only 3 things to Mars to help you survive, what would they be? Let us know in the comments. I'll pin the most creative answer. Now let's begin. Mars has captivated humanity for centuries. We've sent rovers, built orbiters, and dreamed of walking on its surface. Right now, NASA's Perseverance and Curiosity rovers are exploring ancient riverbeds, discovering organic compounds, and even finding bleached rocks that hint at rainfall from billions of years ago. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter continue to study the planet's atmosphere, revealing secrets about its composition and chemistry. These missions tell us something remarkable. Mars wasn't always the barren wasteland we see today. It was once a world with flowing water, a thicker atmosphere, and perhaps even life. But that Mars is gone. What remains is a planet so unforgiving that surviving there for even a single year would push human endurance beyond anything we've ever attempted. Let's talk about the atmosphere first, or rather, what's left of it. Earth's atmosphere is thick, protective, and filled with oxygen.
Mars? Not so much. The Martian atmosphere is about 100 times thinner than Earth's. To put that in perspective, standing on Mars would feel like standing at an altitude of 100,000 feet above Earth's surface. That's more than 3 times higher than commercial airplanes fly. Even the highest peaks on Earth, like Mount Everest, which sits at 29,000 feet, seem forgiving compared to Mars.
At that altitude, there simply isn't enough air pressure to keep your bodily fluids in liquid form. Without a pressurized suit, your blood would literally start to boil. Your lungs would collapse. You'd lose consciousness within 15 seconds and be dead within 2 minutes. This isn't a slow process, it's violent, immediate, and irreversible. But let's say you're wearing a state-of-the-art spacesuit that keeps you pressurized. You're safe from the boiling blood scenario. Great. Now you face the next problem, what you're breathing, or rather, what you're not breathing. Mars' atmosphere is 95% carbon dioxide. There's almost no oxygen, unlike Earth, where oxygen makes up 21% of the air. Carbon dioxide is what we exhale, not what we inhale. Breathing pure carbon dioxide would cause carbon dioxide poisoning almost instantly. Your body would fail to expel waste gases, leading to acidosis, a condition where your blood becomes too acidic. Your brain would swell, your heart would race, and then stop. Even with the best filtration systems, you'd need a constant supply of oxygen, and on Mars, there's no natural source. You'd be entirely dependent on technology that could fail at any moment. Here's where it gets even more fascinating. The Martian atmosphere isn't just thin and toxic, it's chemically active in ways that make it downright bizarre. Thanks to data from the ExoMars Trace Gas Orbiter, we know that Mars has trace amounts of methane, hydrogen chloride, and even molecular oxygen in its upper atmosphere. These gases appear and disappear seasonally, hinting at processes we don't fully understand yet. Some scientists think methane could be a sign of biological activity, though geological processes could also explain it. The atmosphere also contains ozone, but not nearly enough to protect you from radiation. Unlike Earth, where our thick ozone layer blocks harmful ultraviolet rays, Mars' ozone is scattered and weak. You'd be bathed in radiation every single day. Now let's talk about temperature, because Mars doesn't just kill you with its atmosphere, it freezes you too. The average temperature on Mars is around -80 degrees Fahrenheit. That's colder than Antarctica in the dead of winter. But average temperatures don't tell the whole story. Mars experiences wild temperature swings. During the day, near the equator, temperatures can climb to a relatively balmy 70 degrees Fahrenheit. You might think, hey, that's not so bad. But when night falls, temperatures plummet to -100 degrees Fahrenheit or lower. That's a swing of 170 degrees in just a few hours. Your habitat would need heating systems robust enough to handle these extremes, and any failure would be catastrophic. Frostbite would set in within minutes. Your body would lose heat faster than it could produce it, leading to hypothermia and death. The thin atmosphere also means Mars has no real insulation. On Earth, our atmosphere traps heat, creating a greenhouse effect that keeps us warm. Mars lost most of its atmosphere billions of years ago, and without it, heat escapes into space almost immediately. This is why the temperature drops so drastically at night. It's also why dust storms on Mars, despite being planet-wide and lasting for months, aren't as dangerous as they look in movies like The Martian. The air is so thin that even winds reaching 60 miles per hour don't carry much force. They would knock you over, but they would cover everything in fine, abrasive dust that could damage equipment, clog filters, and make life miserable. Speaking of dust, let's discuss what it's made of and why it's a bigger problem than you might think. Martian dust isn't like the dirt in your backyard. It's incredibly fine, almost like talcum powder, and it's everywhere. Worse, it's loaded with perchlorates, toxic chemicals that can cause thyroid problems and damage your metabolism if ingested or inhaled. The Curiosity and Perseverance rovers have detected perchlorates in Martian soil at concentrations that would be deadly to humans. If dust gets into your habitat, onto your food, or into your water supply, you're in serious trouble. And trust me, dust will get in. It's electrostatically charged, meaning it clings to everything. Your spacesuit, your equipment, your habitat walls. You can't escape it. If you're finding this journey through Mars as mind-blowing as I am, make sure to give this video a like. Your support helps me continue exploring the mysteries of our universe and sharing them with you. Now let's consider radiation, one of the most insidious threats on Mars. Earth is protected by a magnetic field that deflects charged particles from the Sun and cosmic rays from deep space. Mars doesn't have this shield. Its magnetic field collapsed billions of years ago, leaving the surface exposed to relentless radiation. On Earth, you might receive about 3 millisieverts of radiation per year from natural sources. On Mars, you'd receive about 250 millisieverts annually, and that's if you're lucky. During solar storms, radiation levels spike dramatically. A single solar particle event could deliver doses high enough to cause acute radiation sickness. Over time, chronic exposure would increase your risk of cancer, damage your DNA, and weaken your immune system. Even inside a habitat, you're not fully protected unless it's buried underground or shielded with several meters of Martian soil. Here's the thing about radiation. It's invisible, silent, and cumulative. You won't feel it killing you until it's too late. Astronauts on the International Space Station, which orbits Earth at just 250 miles above the surface, are partially protected by Earth's magnetic field. Even so, they receive about 50 to 200 millisieverts per year. Mars offers no such protection. You're on your own, bombarded by particles that tear through your cells day after day. Some scientists estimate that a round trip to Mars could expose astronauts to radiation levels approaching the career limit set by NASA. Living there for a year, that's a whole different level of risk. Now here's where the beauty and terror of Mars intersect in the most profound way. We often think of planets as static, unchanging worlds. But Mars is alive with geological and atmospheric processes that remind us how dynamic our universe truly is. Recent discoveries from the Perseverance rover have found rocks bleached white by what scientists believe was ancient rainfall. These aren't just any rocks, they're fragments of a lost world, evidence that Mars once had a climate not entirely unlike Earth's tropical regions. Imagine that, rain falling from Martian clouds, pooling in valleys, carving channels through rock. This happened billions of years ago, and the evidence is still there, waiting for us to read its story. The research team, led by planetary scientist Adrian Broz from Purdue University, published their findings in December of 2025. They analyzed thousands of rocks photographed by Perseverance and concluded that these bleached formations required sustained exposure to water over long periods. On Earth, similar rocks form in rainforests where constant humidity leaches minerals from stone. On Mars, this suggests an environment where liquid water existed on the surface for potentially millions of years. Think about what that means. Mars wasn't just briefly wet, it had a stable climate, a hydrological cycle, and conditions that could have supported microbial life. But something catastrophic happened. The atmosphere thinned, the magnetic field collapsed, the water disappeared, either locked away as ice in the polar caps or lost to space forever. This brings us to one of the most haunting questions in planetary science. Where did all the water go? Mars should have water. We see the evidence everywhere. Ancient riverbeds snake across the landscape. Delta formations in Jezero crater, where Perseverance is currently exploring, show clear signs of a lake that once existed. The ExoMars Trace Gas Orbiter has detected water ice beneath the surface and water vapor in the atmosphere that appears and disappears with the seasons. But liquid water on the surface today? Impossible. The atmospheric pressure is so low that liquid water can't exist. It either freezes instantly or evaporates into vapor. Scientists estimate that Mars has lost the equivalent of a global ocean 140 feet deep over the past 4 billion years. That's enough water to cover the entire planet. So where did it go? Some of it is still there, frozen at the poles and buried underground as permafrost. NASA's Mars Reconnaissance Orbiter has mapped extensive ice deposits just beneath the surface in many regions, but a significant amount of water was literally blasted into space. Here's how that happens. When water molecules rise into Mars' upper atmosphere, ultraviolet radiation from the sun breaks them apart into hydrogen and oxygen. Hydrogen, being the lightest element, escapes into space. Oxygen either escapes as well or reacts with iron in Martian soil, creating the rust-red color we associate with the planet. A recent study published in February of 2026 revealed something astonishing. Dust storms actively accelerate this water loss. During the Northern Hemisphere's summer, intense, localized dust storms can drive water vapor high into the atmosphere, where it breaks down and escapes. This process happened during Martian year 37 in August of 2023, when researchers detected enhanced water vapor concentrations above 40 kilometers, followed by increased hydrogen escape at the exobase. This means Mars is still losing water today, albeit slowly. By the way, if you are finding the atmospheric challenges on Mars fascinating, you'll definitely want to check out my video called "This is Why the Moon Will Never Be a Human Home." The Moon faces similar issues with radiation and extreme temperatures, but its challenges are uniquely different from Mars. I break down why establishing a permanent lunar base might be even harder than you think. You can find that video linked in the description and on the cards above. Trust me, it'll blow your mind. Back to Mars. Let's say you've managed to survive the thin atmosphere, the toxic dust, the freezing temperatures, and the constant radiation. You're living in a pressurized habitat, growing your own food, recycling your water, and maintaining your equipment. You're basically performing a high-wire act where one mistake means death. But here's a challenge you might not have considered: the psychological and physiological effects of living on a planet with a different day-night cycle and lower gravity. Mars rotates at almost the same speed as Earth. A Martian day, called a sol, lasts 24 hours and 39 minutes. That's close enough to Earth's 24-hour day that you'd think it wouldn't matter. But it does. Human biology is tuned to Earth's circadian rhythm with incredible precision. Even a 39-minute difference disrupts sleep patterns, hormone production, and cognitive function over time. NASA studies on Mars rover operations teams who work on Martian time to coordinate with rover activities have shown that people struggle to adapt to the solar cycle. They experience fatigue, difficulty concentrating, and mood changes. Now add in the isolation. Mars is, on average, 140 million miles from Earth. At its closest approach, it's still 34 million miles away. Communication with Earth isn't instantaneous. Radio signals travel at the speed of light, but even that takes between 3 and 22 minutes one way, depending on where Earth and Mars are in their orbits. If you have an emergency, you can't call for help and expect an immediate response. You're on your own for at least 6 to 44 minutes round trip. That delay fundamentally changes how you make decisions. Every choice must be carefully considered because mistakes can't be quickly corrected with advice from mission control. The psychological weight of that isolation, combined with living in a confined space with the same small group of people for an entire year, creates stresses that even the most rigorous astronaut training can't fully prepare you for. Then there's gravity, or rather the lack of it. Mars' gravity is about 38% of Earth's. That might sound liberating at first. You could jump higher, lift heavier objects, and move with less effort. But your body didn't evolve for low gravity. On the International Space Station, astronauts experience microgravity and suffer from muscle atrophy, bone density loss, and cardiovascular deconditioning, even with daily exercise routines. Mars' partial gravity is better than zero gravity, but it still takes a toll. Over the course of a year, your muscles would weaken, your bones would lose calcium, becoming brittle and prone to fractures. Your cardiovascular system would adapt to pumping blood against less resistance, and when you eventually return to Earth, you'd struggle to walk under normal gravity. Some scientists worry that prolonged exposure to Martian gravity could cause permanent changes that make returning to Earth medically dangerous. Your immune system would also suffer. Radiation exposure suppresses immune function, making you more vulnerable to infections. In the confined environment of a Martian habitat, germs and bacteria would circulate continuously. If someone gets sick, everyone gets sick. Medical supplies would be limited. You couldn't just go to a hospital or call a doctor. The crew would need extensive medical training, but even then, treating serious injuries or illnesses with limited resources would be nearly impossible. A simple infection that would be easily treatable on Earth could become life-threatening on Mars. Let's talk about food and water, because you can't survive without them, and Mars offers neither. Every calorie you eat and every drop you drink would need to be produced, recycled, or brought from Earth. The Mars missions we've planned, including SpaceX's ambitious Starship program, targeting uncrewed landings around the 2026 Earth-Mars launch window, envision sending cargo ahead of humans to establish supply caches. But even with pre-positioned resources, you'd need to grow food locally to achieve any kind of long-term sustainability. Growing plants on Mars is theoretically possible. Experiments on the International Space Station have successfully grown lettuce, tomatoes, and other crops in controlled environments. But Mars presents unique challenges. The soil is toxic, filled with perchlorates that would poison any plants trying to grow in it. You'd need to either decontaminate the soil or grow everything hydroponically, using water and nutrient solutions instead of soil. Either way, you're dependent on systems that could fail. Your crops need light, and while Mars receives sunlight, it's only about 43% as intense as Earth's due to Mars' greater distance from the Sun. You'd need supplemental lighting powered by solar panels or nuclear reactors. You'd need to carefully control temperature, humidity, and carbon dioxide levels to optimize plant growth. And here's the kicker. Plants on Earth have evolved to thrive in Earth's gravity and atmospheric pressure. We don't fully know how they'll respond to Martian conditions, even in a controlled greenhouse. Early experiments suggest growth rates might be slower, yields might be lower, and some plants might not grow at all. water recycling would be absolutely critical. You can't waste a single drop. Every bit of moisture from your sweat to your urine would need to be captured, filtered, and reused. The International Space Station already does this with impressive efficiency, recycling about 93% of water. But that's in a carefully controlled microgravity environment with regular resupply missions from Earth. On Mars, you're dealing with partial gravity, dust contamination, and no possibility of resupply for months or years. One failure in your water recycling system could mean dehydration and death within days. You'd also need to extract water from Martian ice deposits, which sounds straightforward, but requires energy-intensive heating and purification processes. Remember, Martian ice isn't pure, it's mixed with soil and potentially contaminated with perchlorates. Speaking of energy, let's address the elephant in the room: power. Everything on Mars requires energy. Your habitat's life support systems, heating, lighting, water recycling, food production, communications, and scientific equipment all consume power constantly. On Earth, we take electricity for granted, flip a switch, and the lights come on. On Mars, generating power is a monumental challenge. Solar panels work, but they're less efficient due to the reduced sunlight and frequent dust storms that cover the panels, blocking light. The Mars rovers use solar power supplemented by radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity. These RTGs are reliable and long-lasting, but they're also expensive, produce limited power, and require radioactive materials that are difficult to manufacture and transport. Nuclear fission reactors offer a more robust solution. NASA has been developing Kilopower, a small nuclear reactor designed specifically for space missions. A single kilopower unit could generate 10 kilowatts continuously for over 10 years, enough to support a small habitat. But nuclear reactors bring their own risks. They require careful maintenance, shielding to protect humans from radiation, and backup systems in case of failure. On Earth, when a power plant has problems, technicians can arrive quickly with replacement parts and expertise. On Mars, you're the technician, the engineer, and the emergency response team all rolled into one. If your reactor fails and you can't fix it, you're living on borrowed time until your backup batteries run out. The beauty of nuclear power, though, is its reliability. Unlike solar panels that depend on clear skies and sunlight, nuclear reactors work day and night through dust storms and winter darkness. This is crucial because Martian dust storms can last for weeks or even months. The global dust storm of 2018, which ended the Opportunity rover's mission, blocked out so much sunlight that the solar-powered rover couldn't recharge its batteries. It went silent and never woke up. If you're relying solely on solar power during a storm like that, you'd be in serious trouble. Your heating would fail, your life support would shut down, you'd freeze or suffocate long before the storm cleared. Here's something that fills me with awe every time I think about it. We are discussing these challenges because we're trying to become an interplanetary species. Humanity evolved on Earth, adapted to its gravity, its atmosphere, its magnetic field, its 24-hour day. We are children of this pale blue dot made from elements forged in stars that died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it came from stellar nucleosynthesis, the process by which stars create heavy elements in their cores and scatter them across the universe when they explode as supernovae. You are literally made of stardust. And now we're trying to take that stardust and make it thrive on another world. It's audacious, beautiful, and humbling all at once, but let's be honest about the obstacles. Even with the best technology, surviving 1 year on Mars means confronting challenges that would break most people. Consider the dust storms we mentioned earlier. These aren't just inconvenient weather events, they're planet-altering phenomena that can completely change the Martian environment for months at a time. When dust fills the atmosphere, it absorbs sunlight and heats the air, creating massive temperature gradients that drive even stronger winds. This feedback loop can cause regional storms to grow into global events that engulf the entire planet. During these storms, atmospheric pressure can change by up to 8% globally. That might not sound like much, but remember, Mars's atmosphere is already desperately thin. Any change affects everything from how your equipment operates to how gases behave in your habitat. The dust itself presents another insidious danger. Recent research from Perseverance's SuperCam microphone has confirmed that dust particles in these storms become electrically charged through triboelectric effects. When billions of tiny grains collide in the wind, they exchange electrons, building up static electricity. On Earth, this creates the occasional annoying shock. On Mars, with its thin atmosphere and lack of moisture to dissipate charge, the buildup can be intense. Scientists detected 55 triboelectric discharge events over 2 Martian years, essentially electrical sparks and crackles in the dusty air. These discharges don't just create static, they drive chemical reactions that produce oxidants and perchlorates in real time. The planet is actively manufacturing toxins through atmospheric chemistry powered by dust and electricity. Think about what this means. You're not just dealing with pre-existing toxic soil. Mars is continuously creating new toxic compounds. Your habitat's filtration systems would need to handle not just dust, but chemically reactive particles that can corrode materials, damage electronics, and poison biological systems. These oxidants are so reactive that they break down organic molecules, which is one reason why finding evidence of past life on Mars is so challenging. Any organic compounds that might have existed have been oxidized over billions of years, destroyed by the very chemistry the planet produces. And yet, in September of 2025, NASA announced something extraordinary. Perseverance had discovered potential biosignatures in a rock sample from a location called Cheyava Falls. The rock contained organic compounds, particularly larger molecules like decane, undecane, and dodecane, which could be fragments of ancient fatty acids. On Earth, fatty acids are produced predominantly by living organisms, though geological processes can create them too. The sample also showed leopard-like spots that scientists believe formed through chemical reactions involving iron and possibly microbial metabolism. Here's what makes this discovery so significant. After a rigorous year-long peer review process, where outside scientists scrutinized every bit of data and analysis, the journal Nature published the findings. This is the mission's best candidate so far for containing signs of ancient microbial life processes. But notice the careful language, potential biosignatures. Scientists aren't claiming they found life. They're saying they found patterns that life could have created, but that require more study to confirm. A follow-up study published in February of 2026 evaluated whether non-biological sources like meteorite impacts could explain the abundance of these organic compounds. The conclusion? Non-biological processes alone couldn't fully account for what was found. That means it's reasonable to hypothesize that living things might have formed them, but it's not definitive proof. To know for sure, we'd need to bring the samples back to Earth for detailed laboratory analysis, which is exactly what the Mars Sample Return mission is designed to do. This discovery fills me with wonder for a profound reason. If life existed on Mars billions of years ago, it means life isn't unique to Earth. It means that given the right conditions, liquid water, energy sources, and chemical building blocks, life can emerge elsewhere in the universe. Mars and Earth were once remarkably similar. Both had thick atmospheres, flowing water, and moderate temperatures. Life thrived on Earth and possibly began on Mars too. But their fates diverged. Earth kept its magnetic field, retained its atmosphere, and became a paradise for life. Mars lost its magnetic field, its atmosphere bled away, and it became the frozen desert we see today. We are looking at what could have been Earth's future, or what Earth might have been if conditions had been slightly different. This is the grand story of the cosmos playing out before our eyes. Planets are born, evolve, and die, shaped by forces beyond our control. Magnetic fields, asteroid impacts, stellar radiation, gravitational interactions, all of these influence whether a world becomes habitable or barren. We exist on Earth not because we're special in some cosmic sense, but because our planet happened to have the right combination of factors at the right time. Understanding Mars helps us understand how fragile that balance is. It reminds us that Earth is precious, that its habitability isn't guaranteed forever, and that protecting our home world should be our highest priority even as we dream of exploring others. Now let's return to the practical challenges of surviving on Mars, because understanding the science is one thing, living with the consequences is another. You'd need to maintain your habitat constantly. On Earth, buildings require maintenance, but you can usually delay repairs without catastrophic consequences. On Mars, a small leak in your habitat's pressure seal could be fatal within hours. The atmospheric pressure outside is so low that air would rush out rapidly, depressurizing your living space before you could react. You'd need redundant systems for everything: air recycling, water purification, heating, power generation. If one system fails, the backup kicks in. But if the backup fails too, you're out of options. Equipment maintenance in Martian conditions is exponentially harder than on Earth. The extreme temperature swings cause materials to expand and contract, leading to metal fatigue and seal failures. The dust works its way into everything, clogging filters, scratching surfaces, and jamming mechanical parts. Electronics exposed to radiation can experience single-event upsets, where cosmic rays flip bits in computer memory, causing glitches or complete system failures. You'd spend a significant portion of each day just maintaining the technology that keeps you alive. It's exhausting, stressful, and relentless. There's no vacation from survival. Then there's the question of what happens when something breaks that you can't fix. On the International Space Station, astronauts have successfully performed repairs using 3D printers to manufacture replacement parts. Mars missions would need similar capabilities, but with far greater self-sufficiency. You couldn't simply order a part from Earth and wait for the next cargo shipment. Depending on orbital positions, it could take anywhere from 6 to 9 months for a spacecraft to travel from Earth to Mars. If you need a critical component, you'd have to either fabricate it yourself using local materials and 3D printing, or find a workaround with what you have. This requires not just technical knowledge, but creativity and problem-solving under pressure. Let's discuss mobility, because you're not going to spend an entire year confined to a single habitat. Exploring Mars, conducting scientific research, and gathering resources would require venturing outside. That means spacesuits, rovers, and dealing with terrain that's both beautiful and treacherous. Martian landscapes are covered with rocks, craters, steep slopes, and fine dust that could hide dangerous obstacles. The rovers we've sent to Mars move slowly and cautiously for this reason. Curiosity and Perseverance travel at maximum speeds of about 0.09 miles per hour. They're not built for speed, they're built for survival and careful navigation. Humans in spacesuits would move faster, but still face significant limitations. Spacesuits on Mars would need to be far more advanced than anything we've used in space so far. They'd need to provide pressure, oxygen, temperature control, radiation shielding, and dust protection, while allowing enough flexibility for you to perform complex tasks. Current spacesuit designs are bulky and limit mobility. NASA's developing new suits for Artemis lunar missions that improve flexibility, but Mars suits would need even more capabilities. They'd need to handle the sharp, abrasive Martian dust that destroyed the seals on Apollo lunar suits. They'd need to function in temperatures ranging from 70 degrees Fahrenheit in sunlight to minus 100 degrees Fahrenheit in shadow. They'd need life support systems that could last for 8 to 10 hours of extravehicular activity, giving you enough time to accomplish meaningful work outside. Every time you go outside, you'd need to perform a ritual that astronauts call pre-breathing. Because Mars suits would operate at lower pressure than your habitat to allow better mobility, you'd risk decompression sickness, the bends, if you went out immediately. Nitrogen dissolved in your bloodstream would form bubbles as pressure dropped, causing joint pain, neurological damage, and potentially death. To prevent this, you'd breathe pure oxygen for hours before each excursion, purging nitrogen from your system. It's time-consuming and limits how quickly you can respond to emergencies. Imagine seeing a dust storm approaching on the horizon and knowing you need to secure equipment outside, but you can't go out for another 2 hours because you haven't finished pre-breathing. That's the kind of frustrating limitation you'd face constantly. Transportation across Mars presents another layer of complexity. Rovers would be essential, but they'd need to be pressurized vehicles that function as mobile habitats. NASA's planning for pressurized rovers that could support weeks-long expeditions away from the main base. These rovers would essentially be small homes on wheels, equipped with life support, sleeping quarters, laboratories, and supplies. But they'd also be vulnerable. A mechanical breakdown far from base could be a death sentence if repairs couldn't be made quickly. You'd need extensive redundancy, backup power, backup life support, backup communications. Every kilogram of backup equipment is weight that could have been used for scientific instruments or supplies, creating constant trade-offs between safety and mission capability. The terrain itself tells stories that would fill you with awe if you had time to appreciate them. Olympus Mons, the largest volcano in the solar system, rises 16 miles high, nearly 3 times the height of Mount Everest. Its base spans roughly the same area as the state of Arizona. The Valles Marineris Canyon system stretches over 2,500 miles long, 4 miles deep, and up to 125 miles wide. If it were on Earth, it would span the entire width of the United States. These are geological features that dwarf anything on our planet, carved by volcanic activity, tectonic forces, and water erosion billions of years ago. They're evidence of a planet that was once geologically active, with magma churning beneath the surface and water flowing above it. But here's what's haunting about those ancient features. Mars is now geologically dead. Unlike Earth, where plate tectonics continuously reshape the surface, volcanic eruptions release gases, and the water cycle redistributes materials, Mars is frozen in time. Its core has cooled, its magnetic field has vanished. The dynamo that once protected the planet shut down roughly 4 billion years ago, and without it, the solar wind began stripping away the atmosphere. Over billions of years, Mars transformed from a potentially habitable world into the hostile desert we're trying to survive on. We're seeing the end result of planetary death, a process so slow that it's measured in geological epochs rather than human lifetimes. This brings us to a critical question. Why did Mars die while Earth lived? The answer lies in size and position. Mars is about half the diameter of Earth and only 11% of Earth's mass. Smaller planets cool faster because they have less internal heat to begin with and a higher surface area to volume ratio, which means they lose heat more efficiently. Earth's core remains molten because our planet is large enough to retain that primordial heat from its formation, supplemented by heat from radioactive decay of elements like uranium and thorium deep underground. Mars simply didn't have enough mass to maintain a molten core indefinitely. When the core solidified, the magnetic field collapsed, and the planet's fate was sealed. Mars' distance from the Sun also played a role. At an average of 142 million miles from the Sun, compared to Earth's 93 million miles, Mars receives only about 43% as much solar energy. This meant cooler surface temperatures even when Mars had a thicker atmosphere. Some scientists theorize that Mars might have been habitable only during volcanic periods when greenhouse gases from eruptions warmed the planet temporarily. Between volcanic episodes, the planet would have frozen again. This creates a picture of ancient Mars as a world with intermittent habitability rather than continuous Earth-like conditions. Life, if it existed, might have been microbial and confined to brief windows of opportunity. Recent climate models published in early 2026 suggest that even with all of Mars' accessible carbon dioxide released from polar ice caps and subsurface reservoirs, the atmospheric pressure would reach only about 20 millibars, roughly 2% of Earth's sea level pressure. The warming from that carbon dioxide would increase temperatures by only about 10 degrees Celsius. To make Mars warm enough for liquid water to exist stably on the surface, you'd need temperatures around 250 to 273 Kelvin, which is roughly minus 23 to 0 degrees Celsius. Current models indicate you'd need to artificially increase the planet's infrared opacity by a factor of 2 to 4. That means trapping heat far more efficiently than carbon dioxide alone can achieve. This is where proposed solutions like super greenhouse gases come in. Scientists have explored the possibility of manufacturing gases like perfluorocarbons or sulfur hexafluoride, which trap heat thousands of times more effectively than carbon dioxide. Theoretically, releasing enough of these gases into Mars' atmosphere could create significant warming, but the scale of production required is staggering. We're talking about industrial operations that would need to produce millions of tons of these gases annually for centuries. A recent paper by Slava Turyshev from NASA's Jet Propulsion Laboratory calculated that achieving breathable oxygen levels on Mars would require oxygenation work exceeding 10 to the 25th power joules. To put that in perspective, that's more energy than humanity currently produces on Earth in several years. You'd need sustained industrial power in the hundreds of terawatts to petawatt range. That's hundreds of thousands to millions of times more than a typical nuclear power plant produces, running continuously for centuries to millennia. The conclusion is sobering. Global terraforming of Mars isn't impossible, but it would require planetary-scale industrial capabilities far beyond anything humanity has ever attempted. We're talking about an engineering project that would span multiple human lifetimes, consume resources on a scale we can barely imagine, and require technologies we haven't fully developed yet. It's not a project for the 21st century or even the 22nd. It's a multi-millennial endeavor that assumes humanity survives long enough and develops sufficiently advanced technology to even attempt it. But here's where perspective shifts everything. While global terraforming seems impossibly distant, regional solutions might be achievable sooner. The concept is called paraterraforming. Instead of changing the entire planet, you create localized habitable zones. Imagine massive domed structures or underground cavities filled with breathable air, warmed to comfortable temperatures, and shielded from radiation. Inside these protected zones, you could grow forests, establish ecosystems, and live without spacesuits. The engineering challenges are still immense, but they're orders of magnitude smaller than planetary terraforming. A single dome covering a few square kilometers would require less material and energy than attempting to alter an entire planet's atmosphere. Researchers believe regional paraterraforming could be accomplished with near-term industrial capabilities, meaning within the next century or two if we commit resources to it. You'd still need to build the infrastructure, transport materials, and construct the domes, but these are engineering problems we understand. We know how to build pressure vessels, life support systems, and radiation shielding. Scaling them up to create city-sized habitats is challenging, but not science fiction. This is the practical pathway to long-term Mars colonization. Start small with pressurized habitats, gradually expand into regional domes, and eventually, if humanity persists for thousands of years, perhaps consider planetary engineering. Living in these early habitats for a year would mean accepting that you're not living on Mars so much as living inside a bubble on Mars. Your world would be confined to pressurized spaces connected by tunnels or covered walkways. Venturing outside would require spacesuits and careful planning. It's claustrophobic, restrictive, and psychologically demanding. Studies of people living in Antarctic research stations and submarine crews give us some idea of what to expect. Confined environments with small groups lead to interpersonal tensions, especially during long periods with no escape. You can't just take a walk outside to clear your head. You can't visit friends in another city or take a vacation. You're stuck with the same faces, the same walls, and the same limited space day after day for an entire year. The psychological term for this is ICE, Isolated Confined Environment. NASA and other space agencies have studied ICE psychology extensively because it's critical for long-duration missions. They've learned that crew selection matters enormously. You need people who are not only technically skilled, but also emotionally stable, adaptable, and good at conflict resolution. Even with careful selection, problems arise. People get on each other's nerves. Small annoyances become major irritants when there's no escape. Someone's chewing sounds, their habit of leaving things out of place, or their way of speaking can drive you crazy after months of constant exposure. Mission psychologists would work with crews remotely, but remember that communication delay. You can't have a real-time therapy session when every response takes 6 to 44 minutes round trip. Depression and anxiety would be constant risks. The isolation, the danger, the sheer distance from Earth and everything familiar, all of it weighs on the human psyche. Looking out a window and seeing an alien landscape instead of blue skies and green trees is disorienting at a deep, primal level. Humans evolved in specific environments with specific visual cues that signal safety and resources: water, vegetation, clear horizons. Mars has none of that. It's rust and rock and emptiness stretching to a horizon that's slightly closer than Earth's because Mars is smaller. The sky is the wrong color. The sun is dimmer and appears smaller. Even the passage of time feels different with sols instead of days. All these subtle wrongnesses accumulate, creating a sense of alienation that no amount of training fully prepares you for. Sleep disturbances would compound the psychological challenges. Despite the Martian sol being only 39 minutes longer than Earth's day, that difference accumulates. Your circadian rhythm, controlled by the suprachiasmatic nucleus in your brain, is remarkably precise. It's synchronized to Earth's 24-hour cycle by environmental cues called zeitgebers, primarily light and darkness. On Mars, those cues are slightly off. The sun rises and sets on a different schedule. Over weeks and months, this desynchronization causes what chronobiologists call non-24-hour sleep-wake disorder. You'd experience difficulty falling asleep, frequent awakenings, daytime fatigue, and impaired cognitive function. Your body would constantly try to reset to Earth time while Mars pulls you in a different direction. Melatonin production, which regulates your sleep cycle, would be disrupted. Cortisol rhythms, which control stress responses and energy levels, would drift out of sync. Even your core body temperature, which naturally fluctuates on a circadian rhythm, would struggle to adapt. Studies of Mars rover teams on Earth who worked on Martian time showed these exact effects. People reported feeling jet-lagged constantly, struggling to maintain focus, and experiencing mood swings. And they were on Earth with the option to return to normal schedules eventually. On Mars, there's no return. You're committed to that soul cycle for your entire stay. Now imagine experiencing all of this while knowing that a single equipment failure could kill you. The psychological burden of living with constant mortal danger is something we understand from other high-risk professions. Submariners, astronauts on the International Space Station, and researchers in Antarctica all face elevated risks, but they also know that rescue is theoretically possible. A submarine can surface, the ISS crew can evacuate in Soyuz capsules if necessary. Antarctic researchers can be airlifted in emergencies. On Mars, there's no rescue. If something goes catastrophically wrong, help is at least 6 months away. You'd need to solve the problem yourself or accept that you're going to die on an alien world, 100 million miles from home. This reality fundamentally changes decision-making. Every action carries weight because mistakes are unforgiving. You can't take unnecessary risks. You can't be cavalier about safety protocols. The pressure to be perfect, combined with the knowledge that you're not perfect, that you're human and humans make mistakes, creates constant background stress. Psychologists call this hypervigilance, and it's exhausting. Your nervous system stays activated in a state of alertness that's meant to be temporary, a response to immediate threats. But on Mars, the threat never ends. You're always one mistake away from disaster, and your brain knows it. Let's talk about something that might seem mundane but becomes critically important in this context. Food. Not just nutrition, but the experience of eating. On Earth, food is more than fuel. It's comfort, culture, social bonding, and sensory pleasure. The smell of fresh bread, the taste of ripe fruit, the texture of a perfectly cooked meal. These experiences connect us to our humanity. On Mars, especially in the early years, food would be functional rather than enjoyable. You'd eat freeze-dried meals, hydroponically grown vegetables with limited variety, and perhaps insects or algae cultivated for protein. The sensory experience would be monotonous at best. Research on isolated groups shows that food becomes emotionally significant in ways it doesn't in normal life. Special meals mark occasions and break up the routine. Sharing food creates social bonds. On long Antarctic expeditions, the quality and variety of food directly correlates with crew morale. When food is boring or unpleasant, morale suffers. When chefs can create something special, even just a cake for someone's birthday, spirits lift. On Mars, you'd have limited ingredients and limited storage for special items. The psychological impact of eating the same meals repeatedly, week after week, month after month, shouldn't be underestimated. It's a small thing that becomes a big thing when you can't escape it. Growing fresh food would help, but it introduces new challenges. Plants need care, which means time and labor. They can fail, diseases, nutrient deficiencies, equipment malfunctions, and when they do, you lose both food and the psychological benefit of nurturing living things. Studies have shown that caring for plants and watching them grow has therapeutic benefits. It gives you something to nurture, a connection to life and growth in an otherwise sterile, mechanical environment, but it also means you can experience failure and loss, which in a survival situation adds emotional weight to what would normally be a minor disappointment. Here's something that fills me with both wonder and melancholy. We're discussing these challenges because humans are driven to explore. It's in our nature. Our ancestors left Africa and spread across Earth, crossing deserts, oceans, and ice fields. They settled in environments as hostile as Mars in their own ways: Antarctica, the Arctic, high deserts, isolated islands. Humans have always pushed into the unknown, even when it was dangerous, even when it was uncomfortable, because we're curious and we dream of what's beyond the next horizon. Mars is the ultimate horizon for our time. It represents humanity's next great migration, our transformation from a single planet species to something more. The challenges we're exploring aren't reasons to give up. They're problems to solve, obstacles to overcome, opportunities to demonstrate human ingenuity and resilience. But we must be honest about the costs. the first people to live on Mars for extended periods will sacrifice enormously. They'll face physical deterioration, psychological stress, and constant danger. Some might not survive. History is full of explorers who died pursuing their dreams. Magellan, Franklin, Amelia Earhart, the Challenger, and Columbia crews. We honor their courage and acknowledge that exploration sometimes demands the ultimate price. The question is whether we're willing to accept that price, whether we value the expansion of human presence in the cosmos enough to risk lives for it. There's also an ethical dimension we can't ignore. Resources spent on Mars missions could be used to address problems on Earth: climate change, poverty, disease, inequality. Some argue we should fix our home planet before trying to colonize another. It's a valid perspective. But others argue that space exploration drives innovation that benefits Earth, that having a backup location for humanity protects against existential risks like asteroid impacts or global catastrophes, and that the human spirit needs grand challenges to inspire us. These aren't mutually exclusive positions. We can work on Earth's problems and explore Mars. It's not an either-or choice, though resource allocation requires difficult decisions. Personally, I find meaning in both endeavors. Protecting Earth is essential because it's our home, the only place in the universe we know with certainty can support life. But exploring Mars expands our understanding of planetary science, climate change, geology, and the conditions necessary for life. Everything we learn about why Mars died and Earth lived helps us understand what we need to protect here at home. Mars is a cautionary tale written in geology and atmospheric chemistry. It shows us what happens when a planet loses its magnetic field and atmosphere. It demonstrates that habitability isn't permanent, that worlds can die, and that the conditions we take for granted on Earth are precious and fragile. The discoveries we've made on Mars have already transformed our understanding of planetary science. The Mars Express mission, launched in 2003 and still operating after over 20 years in orbit, has mapped the planet in unprecedented detail. Its Mars' radar instrument has detected liquid water beneath the southern polar ice cap, potentially a subglacial lake similar to Lake Vostok in Antarctica. If confirmed, this represents one of the most significant discoveries in planetary science because liquid water is essential for life as we know it. Even in extreme cold, buried beneath ice and isolated from sunlight, microbial life could potentially survive by extracting energy from chemical reactions involving minerals and dissolved gases. The ExoMars Trace Gas Orbiter, which arrived at Mars in 2016, has revolutionized our understanding of Martian atmospheric chemistry. Its instruments are sensitive enough to detect gases at concentrations measured in parts per trillion. That's like finding a single drop of water in several Olympic-sized swimming pools. With this sensitivity, researchers have created the first detailed vertical profiles of isotopes in carbon dioxide, carbon monoxide, and water vapor throughout Mars' atmosphere. These isotope ratios tell us about the planet's history, how much atmosphere has been lost, where water came from, and how atmospheric chemistry operates. One of ExoMars' most intriguing and controversial findings involves methane. Earlier missions had detected occasional spikes of methane in Mars' atmosphere, which was exciting because on Earth, methane is produced predominantly by biological processes. Microbes in swamps, rice paddies, and the digestive systems of animals generate most of Earth's atmospheric methane. Geological processes like volcanic activity and reactions between water and certain minerals can also produce methane, but in much smaller quantities. So finding methane on Mars raised the tantalizing possibility of either active biology or ongoing geological activity. However, ExoMars' high-precision instruments have set a detection limit of just 20 parts per trillion for methane, and most measurements come back below that threshold. The methane, if it's there at all, is incredibly sparse and appears in localized plumes rather than being evenly distributed. This creates a fascinating mystery. Previous missions detected methane. The Curiosity rover measured spikes of up to 7 parts per billion in Gale Crater. That's 350 times higher than ExoMars's detection limit, so it should be easily detectable. Yet ExoMars, with its more sensitive instruments, sees almost nothing. How can this be? Several theories have emerged. One possibility is that methane is released from the surface in short-lived bursts, perhaps when permafrost cracks or when seasonal temperature changes allow trapped gases to escape. These bursts might be so brief and localized that orbital instruments miss them while a rover on the ground happens to be in the right place at the right time. Another theory suggests photochemical reactions in the atmosphere destroy methane much faster than models predicted, meaning it doesn't persist long enough to spread globally. A study published in March of 2026 analyzed data from both Curiosity and ExoMars and proposed that dust storms might be the key. Remember those triboelectric effects we discussed earlier, where charged dust particles create electrical discharges? Those same processes could drive rapid oxidation of methane, breaking it down almost as quickly as it's released. This would explain why methane appears in localized measurements but doesn't accumulate in the atmosphere. The planet itself is destroying the methane through atmospheric chemistry powered by dust storms. It's yet another example of how Mars' environment is actively hostile to organic chemistry, which makes the search for past life even more challenging and significant. Now let's return to your survival scenario, because we need to address something crucial. What would you actually do during that year on Mars? You're not just surviving for survival's sake. A Mars mission would have scientific and exploratory objectives that justify the enormous cost and risk. You'd be conducting research that couldn't be done remotely, gathering samples, testing technologies, and preparing the way for future missions. This work would give structure to your days, providing purpose beyond mere survival. Psychological research shows that having meaningful work is essential for mental health, especially in challenging environments. People cope better with hardship when they believe their suffering serves a greater purpose. Your days would likely follow a strict schedule. Mars mission planners have proposed timelines similar to ISS operations, where every hour is allocated to specific tasks. You'd wake up, perform health checks, eat breakfast, then move into work periods focused on habitat maintenance, scientific research, equipment repairs, physical exercise, and meal preparation. Exercise would be mandatory, not optional. In the ISS's microgravity environment, astronauts exercise 2 hours daily to combat muscle atrophy and bone loss. On Mars, with 38% gravity, you'd still need significant exercise to maintain strength and cardiovascular health. That's 2 hours every single day for an entire year, performing resistance exercises and cardiovascular workouts in equipment specifically designed for Martian gravity. Scientific work would include geological surveys, searching for biosignatures, analyzing soil and rock samples, monitoring atmospheric conditions, and testing technologies for future missions. You'd be collecting data that scientists on Earth would analyze for years afterward. The rocks you examine, the measurements you take, the samples you gather, this work would contribute to humanity's understanding of planetary evolution, climate change, and the potential for life beyond Earth. It's noble work, important work, but it would also be tedious at times. Science isn't always exciting. Much of it involves careful, repetitive measurements, meticulous documentation, and maintenance of instruments. You'd spend hours calibrating equipment, downloading data, and performing quality checks. Communication with Earth would be a lifeline, but also a source of frustration. That 6 to 44-minute delay means conversations aren't possible. You can't have a real-time discussion. Instead, you'd send messages and wait. You'd receive news from Earth that's already outdated by the time you hear it. Major events happening on Earth would feel distant and disconnected. Your family and friends would be aging, experiencing life events, going through changes, and you'd experience all of it on delay through recorded messages that feel increasingly surreal as the months pass. You'd watch your loved ones celebrate holidays, mark birthdays, and live their lives while you're frozen in time on another world. Some astronauts on long ISS missions report feeling like they're in a different reality, disconnected from Earth in a profound way. They see the planet from orbit, watch it spinning below them, and intellectually know their families are down there somewhere, but it doesn't feel real. On Mars, this disconnection would be exponentially more intense. You can't see Earth as a disk in the sky like ISS astronauts can. You see it as a bright star, sometimes visible in the Martian dawn or dusk, indistinguishable from other bright objects except for knowing what it represents. Everything you've ever known, everyone you've ever loved, all of human history and achievement, it's all on that tiny point of light. The philosopher Carl Sagan called Earth a pale blue dot when Voyager 1 photographed it from beyond Neptune. From Mars, Earth is even smaller, even more fragile looking. The psychological impact of that perspective is profound, yet that perspective is also transformative. Every human who has seen Earth from space reports a shift in consciousness that astronauts call the overview effect. They describe seeing Earth without borders, without divisions, as a unified whole floating in the darkness of space. They describe feeling a profound sense of connection to all humanity and a responsibility to protect our shared home. Frank White, who studied and documented this phenomenon, found that it often leads to lasting changes in worldview and priorities. Astronauts return from space with a deeper environmental consciousness, a reduced concern for national boundaries, and an increased focus on global cooperation. From Mars, this effect would be even more powerful. You'd see Earth and Mars, two planets, two different fates, two possibilities for how worlds evolve. You'd understand viscerally what we can only grasp intellectually on Earth, that planetary habitability is precious, rare, and fragile. This understanding would stay with you for the rest of your life. You'd return to Earth, assuming you survive and make it back, changed in fundamental ways. Your body would need months of rehabilitation to readapt to full gravity. Your bones, weakened by a year in Martian gravity and the journey there and back, might never fully recover. You might face increased cancer risk from radiation exposure that won't manifest for years or decades, but the psychological and philosophical changes would be immediate and permanent. You'd never again look at the night sky the same way. You'd never take air, water, or moderate temperatures for granted. You'd understand in a way most humans never will that we live on a knife's edge, that the conditions allowing life on Earth are maintained by complex systems we don't fully understand and can't fully control. Let's talk about the journey itself, because we've focused on survival on Mars, but getting there and getting back are equally challenging. A typical Mars mission trajectory using current chemical propulsion technology requires 6 to 9 months of travel each way. That's 1 to 1.5 years spent in a spacecraft, plus your year on Mars, totaling roughly 2.5 to 3 years away from Earth. The spacecraft would be small, cramped, and offer no protection from cosmic radiation beyond whatever shielding you can carry. You'd be exposed to radiation levels far exceeding anything humans have experienced on previous missions. The Apollo astronauts who traveled to the Moon spent only a few days in transit and received relatively low radiation doses. ISS astronauts are partially protected by Earth's magnetic field, which deflects much of the cosmic radiation and solar energetic particles that would otherwise bombard them. But traveling to Mars, you'd be beyond Earth's magnetosphere, exposed to the full fury of space radiation for months. Galactic cosmic rays, which are high-energy particles from distant supernova explosions, would pass through your spacecraft and your body constantly. Solar particle events caused by eruptions on the Sun's surface could deliver dangerous radiation doses in hours if you're unlucky enough to be caught in one without adequate shielding. NASA's current estimates suggest a round-trip Mars mission would expose astronauts to radiation doses exceeding their career limits. The agency sets lifetime exposure limits based on acceptable cancer risk, currently a 3% increase in lifetime cancer mortality risk. A Mars mission could exceed this limit, meaning astronauts would knowingly accept a measurably increased risk of dying from cancer later in life. Some might argue it's their choice to make, that adult astronauts can accept those risks for themselves. But it raises difficult ethical questions about whether space agencies should allow missions that virtually guarantee exposure exceeding safety limits. And it doesn't account for other radiation effects beyond cancer, potential damage to the cardiovascular system, neurological effects, immune system suppression, and possible impacts on DNA that could affect future children. Recent research has revealed even more concerning effects of space radiation on the brain. Studies on mice exposed to simulated cosmic ray radiation showed persistent changes in neural structure and function. The radiation caused inflammation in brain tissue, damaged neurons, and disrupted the connections between brain cells. Animals exhibited behavioral changes resembling anxiety and impaired memory. They struggled with tasks requiring spatial navigation and showed reduced ability to recognize familiar objects. While mice aren't humans and laboratory conditions don't perfectly replicate space exposure, these findings suggest that cosmic radiation might cause cognitive impairment that persists long after exposure ends. Imagine returning from Mars and discovering that your memory isn't as sharp as it used to be, that you struggle with concentration, or that you experience mood changes you can't control. These effects might not appear until years after your mission, making it difficult to connect them definitively to radiation exposure. But the possibility exists based on our current understanding that the radiation you'd receive during a Mars mission could subtly alter your brain in ways that diminish your quality of life afterward. This is the hidden cost of exploration that's rarely discussed in the excitement about going to Mars. We celebrate the achievement while the astronauts quietly deal with the consequences. During the journey to Mars, you'd also face the challenge of living in microgravity for months. The spacecraft would be too small and resource-constrained to spin for artificial gravity, a technology we haven't yet developed for practical use. In microgravity, fluids in your body redistribute toward your head, creating that puffy face appearance astronauts develop and causing what's called spaceflight-associated neuroocular syndrome, or SANS. This condition involves changes to the eye's shape and optic nerve, potentially causing vision problems. Some astronauts experience permanent vision degradation after long missions. The mechanism isn't fully understood, but it appears to involve increased intracranial pressure from fluid redistribution, which physically deforms the eyeball and optic nerve. Your cardiovascular system would decondition rapidly in microgravity. Without the constant pull of gravity, your heart doesn't need to work as hard to pump blood throughout your body. It adapts by becoming weaker and less efficient. Your blood volume decreases because your body perceives it has too much fluid, again, due to the redistribution toward your head, so it eliminates fluid through increased urination. When you arrive at Mars and experience even partial gravity again, your cardiovascular system would struggle to adapt. You might experience orthostatic intolerance, where standing up causes dizziness or fainting because your cardiovascular system can't adequately pump blood against gravity anymore. Muscle atrophy would accelerate in microgravity despite hours of daily exercise. Studies from the ISS show that astronauts lose muscle mass and strength even with rigorous exercise programs. The types of contractions your muscles perform during everyday activities in gravity, simply standing, walking, maintaining posture, can't be fully replicated by exercise equipment in microgravity. You can work specific muscle groups, but the integrated whole-body muscle coordination that occurs naturally under gravity is lost. By the time you reach Mars after 6 to 9 months in microgravity, you'd be significantly weakened, making those first weeks adapting to Martian gravity even more challenging. Then there's the psychological toll of the journey itself. You'd be confined to a small spacecraft with a handful of other people for months. Imagine living in a space the size of a small RV, never able to step outside with the same few people for half a year. Every sound, every smell, every habit becomes amplified. The hum of life support systems would be constant. You couldn't open a window for fresh air. You couldn't take a walk to clear your head. You'd be utterly dependent on technology keeping you alive in an environment that's instantly lethal. A hull breach, a life support failure, a fire, any of these could end the mission and your life in minutes. Fire in a spacecraft is particularly terrifying. In microgravity, flames behave differently than on Earth. They form spherical shapes rather than pointing upward, and they spread along surfaces in ways that are harder to predict and control. Combustion products don't rise away from the flame. There's no up in microgravity, so smoke and toxic gases distribute throughout the cabin. The ISS has sophisticated fire detection and suppression systems, but they're not perfect. A fire on the ISS in the mid-1990s filled the station with smoke and could have been catastrophic if crew hadn't responded quickly. On a Mars-bound spacecraft, months from any help, a serious fire would likely be unsurvivable. Water is another precious resource you'd need to carefully manage during the journey. Spacecraft can recycle water from urine, sweat, and humidity in the air, but the recycling isn't perfect. Some water is always lost, requiring resupply. The ISS receives regular cargo deliveries that include water, but a Mars spacecraft would need to carry everything for the entire journey, achieve near-perfect recycling efficiency. Every shower, if you could even take showers, which on the ISS you can't. Astronauts use damp cloths instead. Every drinking cup, every meal containing water, all of it would need to be carefully rationed and recycled. You'd become acutely aware of water in ways that people on Earth never experience. Food for the journey would be pre-packaged and shelf-stable, similar to what's used on the ISS, but in quantities sufficient for the longer mission duration. Variety would be limited by weight constraints. Psychological research on isolated groups has shown that food monotony becomes a significant morale issue over time. Space agencies have worked to improve space food, but it's still fundamentally different from fresh meals. The textures are often mushy or dry. Flavors can be muted because nasal congestion from fluid redistribution in microgravity affects your sense of taste. Some astronauts report that their favorite foods on Earth taste bland in space, requiring extra hot sauce or spices to make meals palatable. After months of this, the simple pleasure of eating becomes a chore, just another task to complete rather than something to enjoy. Arriving at Mars after this grueling journey, you'd face the challenge of landing. Mars landings are notoriously difficult because the atmosphere is thick enough to create friction and heating during entry, but too thin to rely on parachutes alone for landing large payloads. NASA describes the entry, descent, and landing phase as 7 minutes of terror, the time it takes for a spacecraft to go from the top of Mars' atmosphere to the surface. During this phase, the spacecraft must automatically execute a precise sequence of events: atmospheric entry at thousands of miles per hour, deployment of a massive supersonic parachute, separation of the heat shield, activation of descent engines, and finally, a controlled touchdown. All of this happens faster than the communication delay allows, meaning mission control on Earth can't intervene. The spacecraft is on its own. Previous Mars landers have used various techniques to slow descent. The Mars Science Laboratory mission that delivered Curiosity in 2012 used a sky crane maneuver, where a rocket-powered platform lowered the rover on cables in the final moments before touchdown. It was an audacious approach that worked perfectly. Perseverance used a similar system in 2021. But landing humans requires even more precision and reliability. You need larger spacecraft capable of carrying habitats, supplies, and return vehicles. You need pinpoint landing accuracy to touch down near pre-positioned equipment, and you need redundancy in case systems fail. The engineering challenges are substantial, and the consequences of failure would be catastrophic. Let's assume you land successfully and you step out onto Mars for the first time. This moment would be historic, humans setting foot on another planet for the first time since the Apollo missions visited the Moon. But unlike the Moon, which is a 3-day journey from Earth, Mars is a months-long commitment. There's no quick return if something goes wrong. You're committed to staying until the planetary alignment allows for return launch, which means roughly 1 to 2 years depending on mission architecture. Some mission proposals suggest shorter surface stays with longer total mission durations, while others advocate for longer stays to justify the journey. Either way, you're living on Mars for an extended period with no option to leave early. The first weeks would be critical. You'd be establishing routines, testing equipment in actual Martian conditions, dealing with problems that didn't appear during ground testing, and adapting to the physical and psychological challenges we've discussed. Mission planners would schedule this period carefully, balancing the need to establish the habitat quickly with the reality that you're physically weakened from the journey and psychologically adapting to alien surroundings. Mistakes made during this phase could cascade into larger problems later, so despite the pressure to get everything operational quickly, you'd need to work methodically and carefully. You'd be constantly aware that Earth is watching. A Mars mission would be a global media event with billions of people following your progress. Some would celebrate you as heroes, others would criticize the resources spent on exploration. You'd receive messages of support and encouragement, but also face scrutiny of every decision. This public attention adds another layer of psychological pressure. You're not just surviving for yourself or for your crew. You're representing humanity, demonstrating whether we have the capability and will to become an interplanetary species. The weight of that symbolism would be ever present, even in mundane moments like eating breakfast or conducting routine maintenance. One aspect of Mars survival that deserves deeper exploration is the question of what you'd actually see and experience firsthand. We've discussed the environment in technical terms, temperature, pressure, radiation. But what would it feel like to be there, to walk across that landscape and encounter Mars directly? The first thing that would strike you is the silence. Mars has almost no atmosphere, so sound doesn't travel the way it does on Earth. There's no wind noise like we experience on Earth because the thin atmosphere can't create the same acoustic pressure variations. When NASA's Perseverance rover recorded audio from Mars for the first time in history, scientists were surprised by how muffled and quiet everything sounded. Sound travels differently through carbon dioxide than through nitrogen and oxygen, and at such low pressure, high-frequency sounds are particularly dampened. If you spoke to someone standing a few meters away on Mars, even with the thin atmosphere carrying some sound, they probably couldn't hear you clearly without radio communication. Your voice would sound strange even to yourself, both because of how sound propagates through the atmosphere and because sound would also travel through your spacesuit's internal air and the mechanisms of your helmet. You'd be constantly aware of your own breathing, the hum of your suit's life support systems, and the mechanical sounds of your movements. The exterior world would be eerily quiet, lacking the ambient sound that we unconsciously rely on for environmental awareness on Earth. The visual experience would be equally alien. The Martian sky appears butterscotch or salmon-colored during the day due to dust suspended in the atmosphere. These dust particles, made largely of iron oxide, scatter light differently than the nitrogen and oxygen molecules in Earth's atmosphere. On Earth, blue light scatters more than red, creating our blue sky. On Mars, the process is reversed. Red light scatters off the larger dust particles, making the sky appear reddish-brown. But here's something poetic. At sunset on Mars, the area around the Sun actually appears blue. The Sun's light passes through more atmosphere near the horizon, and in those conditions the smaller particles scatter blue light more effectively, creating a blue glow around the setting Sun. It's the inverse of an Earth sunset, where the sky turns red and orange. On Mars, the butterscotch sky develops a blue halo as the Sun descends. The Sun itself would appear about 2/3 the size it does from Earth, because Mars is 50% farther from the Sun. Sunlight on Mars is only about 43% as intense as on Earth, roughly equivalent to the light level you'd experience on Earth on a very overcast day, but with that strange reddish quality. Shadows would be softer, less defined, partly due to the reduced light intensity and partly due to dust scattering light into shadowed areas. The overall brightness would feel dim, even at noon, contributing to a sense of perpetual dusk. Looking at the landscape, you'd see a world of reds, browns and greys. The iron oxide that gives Mars its rusty color dominates the surface, but there's more variety than you might expect from orbital images. Close-up photographs from rovers show rocks with different compositions. Some are dark basalt from ancient volcanic activity, others are lighter-colored sedimentary rocks formed in water, and still others show evidence of chemical weathering that created minerals like hematite, sulfates, and clays. These different materials create subtle color variations, dark gray to black basaltic rocks, lighter tan sedimentary formations, and occasional outcrops of crystalline minerals that catch the light differently. The textures would vary depending on where you landed. Some regions of Mars are covered in fine dust that would shift under your boots like flour or talcum powder. Other areas are strewn with rocks and boulders of various sizes, the remains of ancient impacts or volcanic eruptions. Some regions feature bedrock exposed by erosion, showing layered deposits that tell geological stories spanning billions of years. If you landed in Jezero Crater, where Perseverance is currently exploring, you'd see the remnants of an ancient river delta, sedimentary fan structures that formed where a river once flowed into a crater lake. The water is long gone, but the geological structures remain, frozen in time, waiting for someone to read the story they tell. Walking across this terrain in a pressurized suit would be a strange experience. Remember, gravity is only 38% of Earth's, so your body weight would be much less than you're accustomed to. After adapting to Martian gravity for a while, you'd develop a distinctive gait, probably a bounding motion where each step launches you slightly upward in a gentle arc. The Apollo astronauts on the Moon, with even lower gravity at 17% of Earth's, developed this exact technique. It's more energy efficient than trying to walk normally, but it would take practice to control your movements. Too much force and you'd leap higher and farther than intended. Too little and you'd struggle to make progress, especially in a bulky spacesuit that restricts movement and adds significant mass, even though it doesn't weigh as much as it would on Earth. Your spacesuit would be your personal spacecraft, your life support system, compressed into a wearable form. Current Mars suit designs are significantly more advanced than the suits used on the Moon during Apollo. NASA's Z2 suit prototype and subsequent designs focus on mobility and durability for extended surface operations. The suit would need to protect you from radiation, provide thermal control, supply oxygen, remove carbon dioxide you exhale, manage humidity and temperature, and allow enough flexibility for scientific work. It would probably feature a portable life support system worn as a backpack, multiple layers of insulation and protective materials, a hard upper torso for structural support, and advanced joint designs that allow better range of motion than earlier suit generations. Even with these improvements, working in a spacesuit is exhausting. ISS astronauts who perform spacewalks report that EVAs, extravehicular activities, are physically and mentally draining. Your hands would tire quickly from working against the suit's internal pressure. Every time you grip a tool or manipulate an object, you're fighting the suit's tendency to maintain its pressurized shape. After several hours of this, your forearms would burn with fatigue. Your shoulders and back would ache from supporting the suit's mass and working in constrained positions. And despite the suit's thermal control systems, you'd likely experience hot and cold spots as your activity level varied and local conditions changed. Imagine conducting geological surveys in this condition. You'd need to collect rock samples, which involves selecting specimens, documenting their location, carefully lifting and manipulating them with gloved hands, placing them in sample containers, and sealing everything properly to prevent contamination. All of this while maintaining awareness of your suit's consumables, how much oxygen and battery power remains, and environmental conditions. If a dust storm approached, you'd need to return to the habitat before visibility dropped dangerously low. If your suit developed a problem, you'd need to recognize the warning signs and make critical decisions about whether to abort the EVA or continue working. The risk of suit puncture would be constant. Mars's surface is covered with sharp rocks broken by impacts and thermal stress. Basaltic rocks in particular can fracture into pieces with razor-sharp edges. Your suit would need to be remarkably durable, but no material is indestructible. A puncture would cause rapid pressure loss. How rapid depends on the size of the hole. A tiny micrometeorite-sized puncture might leak slowly enough that you could return to the habitat before losing too much pressure. A larger tear could be catastrophic, causing near instantaneous decompression that would render you unconscious in seconds. This is why mission protocols would require at least 2 people on every EVA. If one person's suit fails, the other can provide assistance and help them reach safety. NASA and private companies are also developing Mars surface vehicles that would extend your range beyond what's possible on foot. These rovers would be pressurized so you could drive without wearing a spacesuit, essentially mobile habitats that allow multi-day expeditions away from the main base. Imagine driving across Valles Marineris, that massive canyon system we discussed earlier, or approaching Olympus Mons, the largest volcano in the solar system. These features are so vast that approaching them would take days of driving, even with capable vehicles. Olympus Mons is roughly 375 miles in diameter at its base. The caldera at its summit is 53 miles across. These aren't features you can explore in an afternoon. They're the scale of terrestrial mountain ranges or island chains, requiring expedition-level planning and resources. During such expeditions, you'd be even more isolated than at the main habitat. You'd be dozens or hundreds of miles from backup equipment, medical facilities, and the relative safety of your primary base. The pressurized rover would become your entire world for days or weeks. You'd eat, sleep, work, and live in that small vehicle, venturing out occasionally in your spacesuit to conduct surveys or collect samples. The psychological challenge would be similar to polar expeditions on Earth, small groups in confined spaces, far from help, completely dependent on their equipment and each other. The stress of this isolation compounds the stress of the Martian environment itself. If you made this far, please give this video a like. And speaking of the challenges and realities of space exploration, if you're wondering why we haven't returned to the moon despite having done so decades ago, I dive deep into the political, economic, and technical reasons at the video on the screen. It reveals surprising truths about what it really takes to sustain human space exploration beyond just the initial achievement. See you there.